Cool. So thank you guys for coming. My name is Shalin Shekhar Mangar. I work at LucidWorks. I'm one of the committers on Apache Solr and a PMC member. I have been working with LucidWorks for the past 3 years, mostly full-time on Solr. Before that, I worked at AOL, where I worked on a few very large-scale Solr deployments, specifically the one for AOL Webmail. So I'm sure a lot of you are already familiar with Solr. Solr is the enterprise standard for search. We have a lot of Fortune 500 companies who use Solr from day to day. In fact, most likely you already use Solr even if you don't use it directly, because you consume it through some service or some company which internally uses it. It's a full-text search engine. You basically send in documents and you send in full-text queries. You can also facet and do statistics and aggregations on top of that data. You have language detection. It's a completely modular system, so you can plug in almost anything. And in fact, most expert users do plug in things like query parsers or ranking and things like that. Part of Solr is what we call as SolrCloud, which is the system that you deploy on a large number of nodes and which allows you to scale. You can add nodes, you can split shards, you can replicate, et cetera, et cetera. We are specifically going to talk about a new feature which was introduced in Solr 6, that is Parallel SQL. And actually, Parallel SQL is just one part of that feature, because there is a whole building block of streaming transformations and streaming expressions on which the Parallel SQL stuff is built on. So what we are going to do in this presentation is we are going to start from the Parallel SQL stuff, because that's the most easiest to understand. And then I'm going to tell you how to use it with Solr, the already released versions. And then we're going to dive into the internals of this, and we're going to see how it is internally implemented and what it is capable of. Okay. So the first question is, why implement SQL in Solr? Why now? Like, Solr has been around for a long time. So I think the reason mainly is ease of use, because Solr is it's very powerful, but it's also quite complex. So with SQL, you basically have an easy way to query the system, which is very, very well known. There is a whole lot of tooling available which can work with a system that exposes a JDBC endpoint, right? The other thing is, if you have a system which speaks SQL, then internally we can compile it and we can execute that query according to the most efficient way possible. So there's a lot of work being done in that area. I don't think we're quite there yet. We don't do a whole lot of automatic optimization right now, but we have the possibility to do that. So the Parallel SQL stuff is very, very new. It was just released in 6.0. The first point release of it was made actually a week back, 6.0.1, which fixes a few more bugs in it. So it's a little bit rough around the edges because it's still under active development. But the whole thing actually is quite powerful, and it has uses beyond SQL as well, which we are going to see at the end of the slides. So what is Parallel SQL? First of all, why do I call it Parallel SQL and not just SQL? The reason is that any query that you make, first of all, it's a SolrCloud only feature. So it only works with SolrCloud. If you're using the old style master-slave replication, you can't use SQL in that. It has to be SolrCloud. So when you execute a query on SolrCloud, it can actually go to each replica of each shard, ask for a subset of data, and operate on that data, merge the results, and give it back to you. So it all happens in parallel. So this is not there are many systems which do things like that. For example, Hive and Impala and all these systems speak SQL. But they are mostly made for long-running analytical workloads on extremely large amounts of data. And on raw data, which is not pre-processed, like indexed in a search engine. So what's happening here is we can use the best parts of the search engine to do certain things which are most easily done inside the search engine, and then we can do the intensive parts, the ones, for example, the joins and all, which are not done very well by search engines, externally inside a worker collection. And we're going to cover that in a bit. So the SQL is parallelly executed across SolrCloud instances. It is compiled internally to what we call streaming expressions and the streaming IO API. when you write this SQL, the SolrCloud collection that you already have is what is the table. So if you say select star from collection 1 or select star from collection 2 or whatever your collection name is, right? So each collection is automatically exposed as a table in this SQL. And the SolrJ client, the Java client that we have, already ships with a thin JDBC client. It's not completely full-featured JDBC client because there are lots of things inside JDBC which we don't implement. And for that reason, you might find a few tools which refuse to work with Solr right now because they might require some capabilities which we do not expose. So what is happening is people are using one or a few tools as the reference and trying to ensure that we are compatible with them. And you will probably see that list of tools being expanded as this feature becomes more and more mature. So the first one that is being used is the DB visualizer. And there are a few folks who are working to ensure that Apache Zeppelin, which is a visualization tool, basically a notebook-style visualization tool that also works with the Solr JDBC driver. So let's dive into the SQL interface of Solr. There are two ways in which the SQL is executed inside SolrCloud. So as I said, there is probably work which is going to happen which will make some of these decisions automatically for you in the future. But right now, you have to consciously choose between two different implementations depending on the kind of data and the kind of queries that you're going to make. The first one is what we call as SQL over MapReduce. And the second one is SQL over Facets. In the first one, what is happening is, the first one is basically suited for when you have a very high cardinality, and you want to do aggregations, you want to do counts or sum or min or max or things like that on top of it. In the second one, you have SQL over Facets, in which all this aggregation and all this unique the keys are actually computed inside a single Solr instance. So if you're already familiar with facets, what are facets? You get the top terms for a given field sorted by some count, right? So in a way, you are deduplicating them and operating on that data. So if you're doing SQL over facets, then it is using facets to get that top n list and then operating on top of that. Okay? So in that way, it is actually pretty fast. But that doesn't work well if you have to get all the facets, all the top terms out of the index, because that will blow up the memory. When you want to do something like that, it's probably better to switch to SQL over MapReduce and not do SQL over Facets. The SQL where clause is basically a Solr query. So you can do range queries, you can do phrase queries, whatever is possible with Solr. That same kind of query you can actually put inside the where clause. There is also an HTTP endpoint. So you can make a query to /SQL. And we'll see an example here. This is probably a good example. So in this case, what we have is we have a collection which has the Enron data set, if you're familiar with that. Basically, the company Enron, there was a huge email set which was leaked out of it. So each document here is an email. And what we're doing is we are saying, from this Enron data set, I want to find the emails to which the most emails were sent. Okay? So this is giving out a list of addresses to which the most emails were sent out. So you can see we do a group by, we do an order by. There is no where clause, but you can obviously add a where clause here as well. So the where clause, as I said, is basically an SQL query. So you can do a simple term search, you can do a phrase search, you can do a range search, any kind of search that is supported by Solr. So this is also where it slightly differs from a regular SQL expression, because in SQL you could also do some number less than 10, right? But that won't directly work here with Solr. You have to express that as a range query which is understood by Solr. I'm assuming that it's a small limitation and it will probably go away at some point, but right now that is what it is. So if you are going to try this feature on Solr 6.0, then you have to keep this thing in mind. You can obviously provide more than one clause, and you can join them and make an arbitrary Boolean expression out of it, and that will all work. You can also do select distinct. The select distinct is always pushed down it can be pushed down to Solr, or it can do the MapReduce approach, in which case the terms are exported to some worker node where they're aggregated. The stats aggregation actually use the stats component inside Solr. I'm kind of assuming a lot of inside Solr knowledge for this talk. So in case there's something not very clear, please feel free to ask a question during the question time, or you can come meet me after the talk. Because I'm going to talk about stats component and all these things. If you're not familiar with Solr, then you might find it a bit odd. But I think to explain these concepts, I have to skip over certain things. Okay? The stats aggregation are always pushed down to Solr. So the stats component is the one which is going to compute all these aggregations for you. It does a approximate count. It can do min, max, etc., sum, average, all those things. The only exception is when you do group bys. If you're doing group bys, then it's not done by the stats component. It is actually computed externally for efficiency reasons. So you guys are all familiar with SQL. This is nothing special, right? It's just a simple SQL expression. You have a group by, you have a having, you have order by, and all those kind of things. The interesting thing to note here is when you use the MapReduce implementation, you can join across collections. You can even join across different Solr clusters by providing the ZK address. You can even combine data from different external sources. For example, there is a source for an external JDBC databases. So if you can connect to that, you can join data between your Solr instance and the data being kept in some other JDBC compliant database. So this makes the whole thing very, very powerful. You can join between arbitrary data sources. And you don't have to worry a lot about how much data you're joining, because this whole thing does not keep a lot of things in memory. It's all streaming. Okay, so it doesn't spill to disk. It just keeps on streaming data, and it stream sorts the stuff on the fly. So you're not going to be worried too much about how much memory you're going to consume by these joins. It's all just going to work. The JDBC driver, as I said, it's part of the SolrJ jar that we ship with Solr. It already provides SolrCloud aware load balancing, so it knows the cluster state, it knows how many shards you have, it knows how many replicas you have. It will ensure that the query goes to the right place. It will randomly select some node and send the SQL statement to that, which will again pan out the query to all the nodes. You can choose whether you're going to use the MapReduce or the facet style aggregation by specifying a parameter called the aggregation mode. So that aggregation mode is specified as part of the JDBC connect string. So as you can see, you have JDBC::Solr// the ZK connection string, the collection equals to the collection name, and the aggregation mode equal to facet in this case. Okay. Any questions until now? This is just the most simplest usage part of SQL. Yes?
If you would have nested objects in your collection, could you go and make these kind of operations within one collection with a nested data structure?
I don't think the nested data is supported right now. This is just the first cut of the feature. I think it just assumes that each document is basically a tuple. But what you can do is, if you're not going to emit both the parent and the child at the same time, if you're going to emit, for example, just the child documents, then it probably can still work. So if you can structure a query which will emit just the child documents from one place, then you can join it with the child documents of another collection. So that's possible. But it can't execute on a complete block at one time. So with that, let's go a little bit deep into how it is actually implemented. There are 5 important concepts that you need to understand in order to completely use this feature. Thank you. Those 5 things are, there's a streaming API, which is actually almost completely inside SolrJ. There is something called a streaming expressions. You have the concept of shuffling, which is basically partitioning plus sorting and streaming out results. You have something called worker collections, and then, of course, the parallel SQL stuff. So let's go over each of them one by one. So first is the streaming API. The streaming API was actually the first thing that was built. It is actually partially, in fact, a lot of it was already available in the 5x releases, because that's when it started being developed. The streaming API is basically, it's just Java classes. So you use those Java classes to compose queries. You specify your transformations, or if you want to group, or if you want to count, or if you want to sum, or if you want to have a where clause and things like that. So you write code to build that, and then you send it to Solr and say, execute this, and give me the results in a streaming fashion. Okay? So that's basically what it is. And what it operates on are tuples. What's a tuple? A tuple is basically just a list of key value pairs. Okay? So you have a key value, key value, key value streaming in, and the last one is what we call as an end of file tuple. That tuple basically says end of file true. So when you see that, you stop. Okay? So this is all streaming, so you're never sure how many results you're going to get. You always have to look at the last tuple. Okay? So if you find the end of file, you just stop. It's actually very similar to the Java I/O. You basically have wrappers and decorators, and this also works in quite the same way. So there are two parts for this. You have a streaming transformation, and you have the streaming aggregations. Transformations transform the data, so you can do things like group by, roll up, union, intersection, complements, things like that. With streaming aggregations, you perform some functions which collect data over some buckets. So for example, you can do count, average, min, max, etc., right? So pretty simple. Now comes streaming expressions. So what is streaming expressions? Streaming expressions, it's basically a query language which was built to specify. So streaming I/O is great. You can do everything with streaming I/O. The reason why we needed streaming expressions was twofold. The first one was streaming I/O is only accessible to Java developers. You have to write Java code to do anything, and you don't always want to write Java code to do the most simplest tasks. So there should be a way to do more complex tasks without writing Java code, right? The second thing was when you execute an SQL statement on some node, that node has to send that whole thing again to some of the worker nodes or some of the replicas for it to actually be executed. And that is only part of the whole query plan. It's not the complete SQL statement. So we needed a way to represent what is going to happen on each of those nodes or each of those replicas so that they can be executed. So the streaming expression is basically a query language as well as a serialization format for Parallel SQL. And later we'll see that there's some other work being done which it will always also be useful for. So the streaming expressions, when you compile them, they actually compile to the tuple stream objects. Tuple stream objects are part of the streaming I/O API. So tuple stream is basically a stream of tuples which are coming in. As I said, the last one would be an EOF tuple. You can also send a streaming expression directly to Solr or via HTTP. In fact, that is how part of the query plan is communicated to other replicas when your Parallel SQL is being executed. So this is an example of a streaming expression. Again, we are looking at the Enron emails dataset. What it is trying to do here is, it is trying to give you the data of which were the addresses to which flowers were sent from 1-800-Flowers. Or basically, emails were sent from the email belonging to 1-800-Flowers, which is a common flowers vendor in the US. So you have expression equal to search. The collection name is Enron emails. The query is from 1800-Flowers star. So any email matching 1800-Flowers will match this query. The fields that we want is from and to, and we want to sort by the from. Okay? So in the result set, you'll see that you get from 1800-Flowers different email addresses. The two are the addresses from belonging to employees of Enron. And at the end, you see EOF. So the response is actually exactly the same if you were to write a Java program with the streaming I/O API, except that in this case, it is automatically compiled and executed for you without writing any Java code. Okay? And this is probably this is a very, very simple example. You can nest the expressions. So for example, I have this search. I can try to completely nest this within a group by or a count or things like that. So you can create very, very complex nested structures and do a lot of very interesting things with it. In fact, you can also parallelize this. So if you want to, for example, group by, you can do the group by in parallel on different worker nodes. And there is a streaming expression for that also. Okay. So streaming expressions are of two types, basically. The first one is a stream source. So these are the expressions which emit the streams, which can later be consumed, and you can do certain things with it. So for example, you have stream sources such as a search. So a search result will emit the tuples. Or you can have a JDBC source, or a facet source, or a stat source, or a topic source. So what's a topic source? The topic source is a little bit interesting because what it allows you to do is to subscribe to a given query, and then whenever a new document comes which matches that query, you can get a response back. You can get a call back, and then you can do something useful with it. Okay, so this is something which is still new, and it is being flushed out. I don't think it's quite ready to use yet, but it will be interesting how it pans out. The second kinds of expressions are decorators. The decorators they wrap around other stream functions, and they perform operations. So for example, you can do a complement, or a hash join, or a partitioning, or intersect, and interesting things like that, right? So you will, if you, we have the Solr reference guide, in which we have a page which details all the streaming expressions which are available, and that list is expanding. Most, but not all, of the streaming expression functions can be parallelized across different collections. So the ones which can be parallelized usually accept a parameter called workers, in which you say, I want 4 workers, or I want 11 workers, and so on and so forth. And that many number of nodes will be used for the parallelization. Now, with that, we come to shuffling. Shuffling is probably one of the most important concepts because it determines the performance of your streaming expression or your SQL statement. This is where the aggregation mode is actually internally used, because what happens is, so what is shuffling? Shuffling is basically partitioning and stream sorting results. Okay, so you partition the results and you sort them and you stream them. Okay, so the sorting is done by the /export handler. If you guys don't know about the /export handler, it's a request handler inside Solr. It operates on doc value fields. What's a doc value? Doc value is it's a column-oriented store. So basically, all values of a given field sorted and deduplicated, stored together. Okay? So when you have such a data structure available on the disk, if you want to just stream it out in a sorted fashion, it's very easy, right? You just seek to that right point, and you just stream out stuff which is relevant to you. Okay? You might apply a function to figure out which one should be streamed out, but it's extremely fast. So we have a few clients who are actually using this in production, and they tell us that with a few fields, they can do about 800,000 tuples per second per node of shuffling. That's pretty fast. So if you're doing it in parallel across a large cluster, you can do very complex analytical queries and still get results in sub-second or a few second times. Okay, and that's pretty powerful. So the sorting is done by the /export handler. You must use doc values for the fields which you want to use here. That is a limitation. But I think using doc values in general is anyway a good idea if you're using complex faceting or sorting, etc. The partitioning is done by what we call a hash queue parser plugin. It's basically a hashing function. You basically give it the number of worker nodes, and it uses one or more fields values. So it goes over the value for each document, applies the hash function, sees on which worker node that hash function's value falls to, and then that worker node will emit value for that particular document. So if you have 5 workers, each worker gets 1/5 of the total results to process. So that is how it happens internally. The moment you send a request to the /export handler on a given node, it basically starts streaming instantly, and it just keeps on streaming until the data ends. Okay, so on the worker node, starts getting the data almost immediately, and it can start doing useful stuff with it. So this is not really a replacement for Hadoop or basically Hive or all those kind of systems where you have to wait for minutes. It is not built for that purpose in mind. It is built where you have a decent or a large amount of data in Solr, and you want to do stuff which maybe takes a few seconds or sub-seconds. It's not suitable when you want to do some stuff which is going to take minutes and minutes of your time. Okay? So because it's all streaming, it's all pretty fast. And the good thing about this is, because it is all streaming and it is all happening really fast, and it is happening in parallel, if you can afford to throw a lot of hardware at it, you can scale it really well. So even if you have very, very complex queries, you can still get the data, you can still get your responses in a small amount of time, because you can use all that hardware. So all replicas shuffle in parallel for the same query, which allows for very large throughputs. The worker collection is basically, it's just a made-up name, really. The worker collection is just like any other SolrCloud collection. It doesn't even have to be a separate collection. By default, it is the same collection which holds the data which you are trying to operate on. But if you really do want to separate the major processing from the place the data actually lives, then you can create a new collection and say that this is my worker collection, and then all the difficult stuff, all the major processing, the aggregations will happen on those nodes. Okay? So by default, the worker collection is the same as the collection which holds your data, but you can choose to separate it out. Okay? So this guy performs the aggregations. There is an HTTP endpoint called /stream, which has to be available. And actually, that endpoint is by default available in Solr 6 on all collections. So you don't have to do anything extra or anything special to enable this. As I said, it might just be empty, or you might just create it just in time, or you might just keep it around with some empty nodes and not use it for any other purposes. When you send in an SQL to Solr, what happens is we use the Presto SQL parser, which is a parser created by Facebook. So that parser internally compiles that SQL statement to the streaming I/O APIs. The streaming I/O APIs are serialized to streaming expressions and then sent to each worker nodes. And the worker nodes make requests to each replica of each shard and get the appropriate data out of it for further processing. So here we have a diagram which shows. So this is an example where we are going to use the aggregation mode of MapReduce. So the client sent an SQL statement to the /SQL handler on some node. This can be any node, part of the collection, away from the collection. As long as it's inside the cluster, you're good. So in this SQL statement, you probably had 5 worker nodes as part of a worker collection. So you have 5 workers. So this is an interesting difference between a regular distributed search and this SQL execution. In a regular distributed search, Solr would choose one replica from each shard, right? And it would send the query to that replica, get the responses from all the shards, merge, and give it back to you. So at any given time, your query is using one replica from each shard. But in this case, your query is using all the replicas from all the shards. Okay? So by adding more replicas or by splitting and creating more shards, you can put massive amounts of computation power behind a single query, which means you can do very complex stuff very, very fast. Okay? So this is an interesting difference between the regular distributed search and this one. So you have the SQL handler which parsed the query, created a streaming I/O representation of it, which was serialized to streaming expressions. That expression was sent to each of the worker nodes. The worker nodes, again, requested data by using the /export handler, or maybe they used the facet method in case you were using the facet method. In this case, we're not. So they will send requests to one replica from each shard. Every worker will get 1/5 of the overall data to process. They will roll it up, and then they will send the whole response back to the SQL handler. So this is all happening in a streaming fashion. There's nothing which is being kept to memory or being spilled to disk here. Okay? So any questions until this point? Yes?
How do you scale the amount of queries? Imagine you have a very expensive query and you allow it to a large user group. If you utilize all replicas everywhere, how do you schedule your I/O capacity, basically? It's totally possibly to jam everything, just 10 users.
Yeah. So this is probably not going to be useful if you're also going to use it for real-time queries, because you're basically going to suck up all the bandwidth available, right? But then this example is an example of very high throughput, very high cardinality aggregation happening on a lot of data, in which case you want all that computation power, okay? So again, it depends on your use case. If you probably wouldn't want to, see, anyway, it's a bad idea to mix very heavy analytical workloads with real-time query workloads, right? That's probably a good advice. So you have to separate them out anyway, okay? So this would probably be a bad idea for the use case that you describe. Yes?
This is maybe a follow-up. Do you see any, for the future, do you think that those features will merge with the classical full-text search, or will those stay separate? Or are there any benefits of using, like your example with the streaming expression, it was a classical search. Do you see any benefit of using it for a search?
Well, it depends. For example, if you have heavy distributed join requirements, then this probably would be the only way to do it, unless those features also get it. See, the problem is when you have distributed joins, it becomes more and more difficult to specify it as part of a classical Solr query. This way, it's much more easier, because you can nest stuff and build more complex expressions. So in fact, I know of someone who is actually using it for regular search, actually planning to use it for regular search. The only drawback here is, because it is streaming, you are not going to get, you're not going to know the number of results to show to the user. So you can, even right now, you can use it as a replacement of classical Solr query, but there's a limitation to it. No, there's no pagination here. So you can provide a limit clause. If you're using SQL, you can do a limit, and you can say, I just want the top 100 results. So if you actually, in fact, if you actually provide a limit clause, then you don't really have to operate on doc values. You can also get the stored fields, and you can also use the regular Solr ranking. But if you want to do analytical stuff, and then you can do exports of the complete data sets. So exporting complete data sets has not been a very strong point of search engines, which is why the cursor mark feature was developed into Solr that allows you to paginate very deep. But this guy is actually built for streaming out entire result sets. Yes?
Why the Presto parser was selected over the Apache Solr, for example? Because in this case, you get the JDBC for free without implementing it yourself.
That's a great question. So why was the Presto parser picked? I think the reason that Joel, who initially wrote this system, gave was, so he considered Calcite as well, but Calcite was far more involved because it had its optimizer and all those things. So the API was far more difficult for him to grasp at that time, and he just wanted to get something up and running. In fact, now there is a Jira issue where he wants to move away from Presto and start using Calcite because he wants to use that optimizer and all this stuff. Yeah. So it's actually in one of my slides on the next things, which are, yeah. All right. So just a quick 2 minutes on what's next, what's happening. So in 6.1, you will see graph traversals with streaming expressions. So this is interesting because right now you have seen that Parallel SQL is compiled to streaming expressions. What they plan is eventually to have a Gremlin language implementation, which is also compiled to streaming expressions. So then you'll have a Gremlin language implementation inside Solr, which can do distributed graph traversals across collections, maybe. Okay. So we already have a function for shortest path. We also have functions for random node walking. You can provide a query, provide filters, and start walking nodes and collect all the nodes. You can also record all the edges and then use it in some place. There is already a GraphML response format. So if you want to visualize it in something which understands GraphML, you can do that. And this is just the start. You'll probably see a lot more happening in the graph part. This is probably its own talk, on its own. This is such a vast topic. The second interesting thing is there is an implementation of a logistic regression query, which is implemented as a streaming expression. So you can use documents inside Solr to train models, and then you can use them in some other way. And how you can use them is you can probably use the topic streams that I mentioned earlier. You can subscribe to something, get an alert, execute that document against a model which is already trained, and then make some decision and send some alert to some place. So for example, you can see, hey, this document is very, very important to me, or maybe that customer wants it, or something maybe more complex. So I think some of the use cases behind all these things are not quite clear even to the people who are implementing this. They're implementing this because seriously, I don't think the use cases are quite clear to them. It's possible now, whereas it was not possible or it was not very easy earlier. And I think people are just waiting to see what kind of use cases the users come up with. Okay? And then the development will probably adjust automatically. Because I know there was the logistic regression part and the graph traversal part was started almost at the same time, but there was a lot more interest in the graph traversal part, so that's where the focus happened, and it's actually going to be released with 6.1. It's already committed to the Solr master branch right now. So you're probably gonna see the logistic regression and some other algorithms implemented as more and more people get involved and start building stuff with it. You can do alerts using the topics and the model streams. There is also something called a Daemon stream. A Daemon stream is something which is like a daemon. It is running all the time. Okay, so you have a new document coming in, it's mashed, that Daemon stream can actually send that alert to you. So it's not just based on a request, it's something which is there all the time and can do stuff in the background. You also have something called an update stream. So right now it's just for queries, but hopefully we will also support things like select into, so you can do some Solr query, some SQL query, and then get the responses and probably update it into a different, or maybe the same Solr collection. So that should also be possible very, very soon. As I said, calcite integration is being worked on. Presto is going to go away. It will be calcite all throughout. JDBC support is being expanded. More and more new kinds of tools are being supported and certified. And the topic stream and model stream are also going to be used for publish, subscribe. So there are lots of ideas. There are lots of Jira issues which are open. A lot of them don't have patches right now. Some of them do. Some of them are already committed. This is actually a great time to get involved with this feature, because even we don't know where it is going to go. I think it's all dependent on what users build with it and what is the interest of the community. So with that, I'm going to close this presentation. Do we have time for questions?
Thank you, Shalin. I think we have time for only one question.
OK.
No questions? Probably they can reach out to you offline.
OK.
We have a coffee break anytime.
All right.
Thank you so much.
Thank you so much for coming. Thank you.